Hi, it's Grace again. I'm professor of mechanical engineering with a focus in materials and biomechanics. And this is the second video that I wanted to share about a particular material property called fracture toughness. And in the last video, I talked a bit about how different materials fail, the types of ways that we see failure. And one of the failure types that I emphasized was fracture, where you have a material that will break in two or more pieces. And you can see this for different types of materials, whether it's glass, ceramics, polymers like the climbing hold, or even metal components as seen in the bridge of the steel beam. And what I demonstrated in the last video was that fatigue loading can lead to fracture. And I showed this with the Menchie's card, which is a plastic card that after many, many cycles, you end up developing a crack initially, and this crack will propagate through and result in catastrophic failure or fracture, as we call it. And this is true for all types of materials, whether they're hard materials or really strong materials as well, meaning that they can fail at loads much lower than their maximum strength. So often we think about a material and the maximum strength that can be applied to failure, a single overload event. However, for any kind of material that experiences thousands or millions of loading cycles, fatigue becomes a particular issue here. One of the things that we did see from the card was that there was a crack that initiated, and that crack grew over time with multiple cycles until it went to the other side. Some types of materials are really good at continuing to withstand loads, even with a large crack in it, and others are not very good at withstanding loads once a crack or a defect has been introduced. And so as engineers, we refer to this as the fracture toughness of the material. How well is the material able to withstand presence of a flaw or defect, such as a crack? This graph is a bit noisy, so I'll walk you through it. On the x-axis, we have the strength of a material, basically how strong that material is. This is what we know intuitively, that metals up here in this area are stronger than polymers or foams, which are down here on the left-hand side. And as we go up on the y-axis, we have an increase in the fracture toughness, which is a measure of a material's ability to withstand fracture even when a crack is present. So on the bottom right corner, we have polymers. We have really soft materials of foam. With foam, you can see me deforming it, and you can see it stretching and getting narrower in the width. And I can pull on it, and it's not failing, so there's no single overload. But as soon as I introduce a crack and I pull on it, I can start to hear it separating when I give it the same amount of pulling strength. And if I keep pulling it, this is now fatigue loading until I get catastrophic failure. At some point, it was able to withstand a crack, but that crack got large enough at some point that it traversed all the way through. Now, if we compare the polymer foam that I was able to break with my hands versus a polymer foam, which would be up here, both stronger and have a higher fracture toughness, we can see how a climbing hold might be able to withstand a crack propagating all the way through up until about this point. This is where I stopped seeing those fatigue lines before catastrophic failure occurred in this hold. So now let's look at polymer holds, indoor climbing holds, for example, versus some common rocks. We can see that common rocks, which is shown by the purple oval circle, is stronger than polymer holds, and we know this intuitively, meaning that the purple oval is more to the right than the teal circle, but that the polymer holds are actually able to withstand cracks much better than common rocks are, meaning any type of flaw or defect in the rock, as we apply more load to them, they are more susceptible to failure, to breaking off the hold or off the rock. And I thought I'd provide some specific numbers here in this table for some of the rocks that climbers are familiar with, as well as some common materials like glass, polyurethanes, aluminum, and steel. These numbers are very difficult to get because the experimental setup is quite difficult. It's not as common as, for example, the strength of a material that can be easily calculated from a tensile test. Briefly, to measure the fracture toughness, you would set up a material where you create a notch, essentially what I did with this polymer strip, and then apply multiple cycles to track how the crack propagates over time and how many cycles and how much energy is absorbed by the material. And what we can see is for rocks, the values range from about 0.1 to a little over 1. The polymer holds that are in the gym are about an order of magnitude higher, around 1 to 2. And then materials that we often see in large structures are much higher than that. And so you can see why engineers really like using aluminum and steel alloys, because their fracture toughness is so much higher and they can withstand multiple cycles even with a flaw present, whether that flaw is a crack that initiated from fatigue loading or is a stress concentration due to holes drilled into the material. And the last thing I want to comment on is where common rocks is on this graph. And we have these lines here because materials tend to follow this type of upward trend. The stronger the material, the better it is at resisting cracks or flaws, at greater fracture toughness. However, you see some materials actually follow this other slope here. And these are brittle type of materials, glasses, pottery, and common rocks. So even though they are stronger, their resistance to cracks is much lower. Their fracture toughness is lower than what you might expect for its strength. And that's all I have for now in terms of fatigue loading and how that can lead to fracture and how we think about different material types and the different properties that those materials have. Enjoy climbing.